So in this video lesson, I'm going to look at an approach that I use to attempt these questions, these long questions on organic structure and naming that you will encounter in your final exams. These are from NSC papers. This particular question is from the DBE or the NSC November 2021 grade 12 final matric exam paper, paper 2. So this is the standard that you will encounter in grade 12, but you will also encounter it in grade 10 and 11 at our school. So let's start off by looking at the format. So if you look at the format of this question, you will see that you encounter a table, and this table has got various compounds in it, organic compounds, and they have letters. So we've got here A, B, C, D, all the way up to H. Some of them are explicitly represented in structural formulae or structural diagrams. So we can see here that this is explicitly a carboxylic acid because of the carboxyl group. Here we have a compound that has got a double bond in it, and we have a methyl group in it as well. So we can see that this is an alkene with a branch. This one is represented in condensed structural formula format and not so easy to identify it. And so I suggest that when you get these tables that you expand those compounds that are not in the structural formula or structural diagram format, that you explicitly do that. This one as well as this one. This one's a little bit easier. Here we have the names of these compounds, so we can see clearly that that is a ketone and that is an aldehyde. So that's what I'm going to do. I'm going to start off by taking C, D, E, F, and H and drawing their structural diagrams. So starting with C, I'm going to start here. So we've got C, and we've got 3 hydrogens. So it's 1, 2, 3. I'm going to put the hydrogens in. Then we have the next C there, and it's got 2 hydrogens attached to it. Then we have another C, and it has 2 hydrogens attached to it. So this is the third C, got 2 hydrogens attached to it. Then we have the next C, but now this C and this C are going to be connected together, and this C has got 3 hydrogens attached to it. But what we want to focus on now is what do we do here? Now, using the circle test around carbons, we have got 1, 2 bonds already around this carbon, and then we need 3 and 4. But now we are connecting the carbon to oxygen, and oxygen has got a valency of 2. So the oxygen is going to form 2 bonds with the carbon. So explicitly what we're going to have here is C double bond O, and that's the carbonyl group. So now we look at this and we can say, well, this is quite clearly a ketone, because we can see that the carbonyl group is inside the chain. It's not on the ends, but it's inside the chain. So this is a ketone. Then we go to D. So to D now, we look at the carbons. We see that D has got 2 carbons, so it's C and C. There are 6 hydrogens. So we're going to go 1, 2, 3, 4, 5, 6. And now we have a saturated compound with no double bonds, and we've got 6 hydrogens. That's great, but where do we fit the oxygen? There's no place to fit the oxygen. So what we need to do is we need to remove one of the hydrogens, which I'm going to do here. And we are going to put the oxygen in here. And remember, oxygens have got a valency of 2, so they will form 2 bonds under normal conditions. And the hydrogen then bonds, the 6th hydrogen bonds with the oxygen. So what we're sitting with there is a alcohol. Now, one might ask, well, is there not necessarily another way of doing it? Well, there actually is. We could also have done it like this. We could have popped the oxygen in between the 2 carbons and then placed 3 hydrogens on each of the carbons at the end. So if we use our circle test, this carbon, 1, 2, 3, 4, that's fine. This carbon, 1, 2, 3, 4, that's fine, and the oxygen is 2. So this is an isomer. As a matter of fact, this is a functional isomer, and this so happens to be an ether. If I'm not mistaken, dimethyl ether. There's 2 methyl groups on either side. However, we are not working with ethers in the NSC syllabus, so this is not an option for us. It's not incorrect, but it's not inside the syllabus, not within the syllabus. So we are going to work with the alcohol. You might be asking, well, could we not have put the hydroxyl group down here or on this carbon? You could, but it would make no difference because this is ethanol. And if we put the OH on this carbon, then it would still be ethanol, and it would still be on carbon 1 because we would just switch from numbering like this, 1, 2, to numbering like this, 1, 2, if the OH is on this carbon. So that is ethanol that we have there. Now we move on to C2H4. Now, C2H4 is an alkene because this satisfies the general formula for alkenes, CnH2n. And if we draw it, we'll see that there is no option other than the fact that it is ethene. So we take the 2 carbons and we bond them together. There we go. We've got 4 hydrogens. There we go. And now when we use the circle test around carbons 1, 2, 3, we need another bond. 1, 2, 3, we need another bond. So we are going to put the double bond in there, and so quite clearly that is ethene. Now, when we go to F and H, we are now going to draw their structural formulae. We see here, so this is butane 2-one. So but is, it's meth, it's eth, it's prop, it's but. Right, and the 2-one tells us that the carboxyl, sorry, not the carboxyl group, the carbonyl group is going to sit on carbon number 2. There we go. And each of these carbons is going to have 4 bonds. So we just use the circle test again. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. That's all fine. And we have 3 methyl. We have 3 methyl. So we go to carbon number 3 and we add a methyl group. And then we fill up with hydrogens. So we have hydrogens there, and there, and there, and there, and there. And so that is 3-methyl-butane 2-one. Now, let's look at 3-methyl-butanal. So if we look at butanal, it's also going to have 4 carbons, 1, 2, 3, 4. And because it's an aldehyde, we are going to put the carbonyl group on carbon number 1. So it's 1, 2, 3, 4. Now we use the circle test. We go 1, 2, 3, 4. So there needs to be a hydrogen on that carbon. 1, 2, 3, 4. So we need another 2 hydrogens there, and then we have 1, 2, 3, 4, and 1, 2, 3, 4. So we need to put hydrogens there, and there, and there, and there. And I hope that you can see, sorry, we've left out the 3-methyl, so let's not, we still need to add the 3-methyl, apologies for that. So that's butanol, and then we add the methyl group on carbon number 3, and I hope that you can see that these are actually isomers of each other. Each of them have got 4 carbons, 1, 2, 3, 4, 5 carbons, 1, 2, 3, 4, 5 carbons, and they've got the same amount of hydrogen. So each of these would have a molecular formula of C5, hydrogens 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's do that again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So it's H11, and then 1 oxygen. Right, so if we do it for the bottom, we work out the molecular formula for the bottom compound, 1, 2, 3, 4, 5, C5. Then hydrogens, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I must have counted wrong up here. I'm going to start there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Apologies for that. Right, so this is H10. So that's going to be, let's make that H10 and 1 oxygen. So counting here, we start here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's also H10 and 1 oxygen. So these are definitely isomers of each other. So now that we've done this, you might think, well, wow, we've spent a lot of time on this and we haven't answered any questions. But what one has done is one has actually prepared yourself to launch into the questions and answer them very, very quickly. So now we're going to move on to the specific questions, and you will see that we'll be able to answer them quite easily. So now we look at question 2.1. It says define the term unsaturated compound. An unsaturated compound is a compound that has double or triple bonds in it. So it's an organic compound. It's got carbons and hydrogens in it, and it has no double bonds. Sorry, it has double bonds and triple bonds, so therefore it's unsaturated. Question 2.2.1, the letter that represents the unsaturated compound. So now, if we go back to what we've solved, let's take a look at that. So I'm going to move this over, and then I'm going to bring in what I have already solved. I'm going to bring it in there. Then what we can see is we're looking for a letter that represents an unsaturated compound. Well, an unsaturated compound's got a double or a triple bond in it. So we can actually see immediately that this is an unsaturated compound because it's got a double bond in it. But we also have another compound that is unsaturated, and that would be E. So we have 2 answers. We can say that the answer to this is B. We've got B is an alkene, and we have that E is an alkene. So the answer to that would be letter that represents an unsaturated compound. So the answer there would be B or E. Either one of them would be correct. They are unsaturated because they've got double bonds in them. The name of the functional group of compound C. Now that we have expanded compound C, we can see there that we quite clearly the functional group is that. So it's the functional group of a ketone they've asked us for C. It's the functional group of the ketone, so that's going to be the carbonyl functional group. That's the carbonyl functional group. C double bond O. The next question is the letter that represents a chain isomer of compound C. Now, if we go to compound C, we look at compound C, we have compound C, we've expanded compound C, as you can see there. Now we're looking for a chain isomer of compound C. So if we look here, we see, okay, we have, in compound C, we've got 1, 2, 3, 4, 5. We have 5 carbons, and we have a carbonyl group. Now, if we look down here, and this happens to be a ketone. So a chain isomer is going to also be a ketone, but it's going to have a different chain. So if we look here, and this is the nice thing about solving the table, if I can use that term, before answering the questions. Can you see we've got 1, 2, 3, just look here, we've got 1, 2, 3, 4, 5 carbons, but this carbon is now in a branch, but here we have the carbonyl group. So this is a ketone because it's sitting not on the ends, then it would be an aldehyde, but on the inside of the chain. So we can say here that C and F are chain isomers of each other, as opposed to the fact that this compound would be a functional isomer of C. And the reason why it'd be a functional isomer of C is because it would have the same molecular formula, and we can see that. We've got, this is going to be C5, the molecular formula, and the amount of hydrogens is starting here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It's going to be H10, and it's going to be O. So it's definitely an isomer of this compound. C is an isomer of F and H, but they've asked us for a chain isomer. So a chain isomer will be F because it's also a ketone, as opposed to H, which would be a functional isomer because it's an aldehyde and this is a ketone. So we can say that the answer is F. So what is the letter that represents the chain isomer of C? And that would be F. Now, I think it would be quite difficult to actually unravel that if we hadn't done this already. So that's why I suggest that we do that. The IUPAC name of compound G. So if we look at the IUPAC name of compound G, so G has been explicitly written in structural formulae. We have the structural diagram, so we can now go and say, okay, well, let's look at the longest chain. The longest chain has got 5 carbons, so we've got there, not 5, it looks like 6. It's looking there, it's 1, 2, 3, 4, 5, 6. Let's count again, 1, 2, 3, 4, 5, 6. So that is going to be hexane. So we've got, if I draw it to the left here, so our carbon backbone is going to be hexane because of the 6 carbons. There are no double bonds, so there's no ene or no triple bonds, there's no yne. But now we must be careful because there is a methyl group. We have a methyl group there. Here we have a chlorine, and we have a chlorine there as well. So that now is a halogen substituent. Let's just be very careful that we don't miss anything. Hydrogen, 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 methyl group hydrogen, chlorine, hydrogen, 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 chlorine. So we've got 2 chlorines. So this is definitely going to be dichloro, and it's going to be methyl. Now comes the tricky part, because we've got to decide how we are going to number the carbons. Are we going to number the carbons from left to right, or are we going to number the carbons from right to left? So let's take a look at that. So if I number the carbons from left to right, 1, 2, 3, 4, 5, 6, then the dichloro is going to be, we're going to describe the position of the chlorines by the carbon number 2 and carbon number 5. So this is going to be 2, 5 dichloro. So you see there, this chlorine's on carbon 2, this chlorine's on carbon 5, and the methyl group will be on carbon number 3, so that would be 3-methyl. If, however, we numbered from right to left, so we numbered like this, 1, 2, 3, 4, 5, 6. Well, now we see that the chlorines sit on carbon number 2 and carbon number 5. That's great, so that's the same. Carbon 2 and carbon 5, so that doesn't seem to make a difference. 2, 5. But now the methyl group is going to sit on carbon 1, 2, 3 on carbon number 4. So this is going to be carbon number 4. So it's going to be 4-methyl. Now, we need to look at the set of numbers which are the descriptors of the positioning of the substituents for the hydrogens, where the chlorines and the methyl group are. So if we look at this set, it consists of 2, 5, and 3, as opposed to this set, which comprises of 2, 5, and 4. So 2, 5, and 3 is a set of 3 numbers that comprises of numbers that are either equal to or smaller than the set of numbers from right to left. So right to left, we've got 2 and 5 and 4. So the difference is that from left to right, the methyl is described by 3, but from right to left, it's described by 4. And so therefore, we are going to number from left to right, because that provides the set of number descriptors that are lower. So therefore, we now can say, all right, now we are going to name in alphabetical order for the substituents. So we're going to start with chloro. So this is, and we don't take the di into consideration when we look at the alphabetical ordering. So this is going to be 2, 5 dichloro. So 2, 5 dichloro. It's going to be 3-methyl. 3-methyl. So there we go. Just stick with my color convention. 3-methyl. So there we go. And then we put the name of the carbon backbone, hydrocarbon backbone, at the end. So it's 2, 5 dichloro 3-methyl hexane. And if we look at the mark allocation, it's 3 marks. So it would more than likely be a mark for the 2, 5 dichloro, a mark for the 3-methyl, and a mark for the hexane. Now, 2.2.5. The general formula of the homologous series to which E belongs. Now, the homologous series is the family of organic compounds. So it's not the functional group. One must be careful not to mix them up. So if we look at compound E is an alkene, and we can see that it's an alkene because there is the structural formula. So the alkenes, as we've already mentioned, their general formula is for when there is a compound that has a single double bond. So that's going to be CnH2n for the alkenes. And we can see that it satisfies that because we have C2 2, N is 2, 2 carbons, and 2 times 2 is 4. So now let's go back and see now what is the next question. So the next question is also a definition. Define the term functional isomers. So functional isomers are compounds that have the same molecular formula, but they comprise of different functional groups. So aldehydes and ketones often form, with the same amount of carbons, form functional isomers, and carboxylic acids and esters with the same amount of carbons form functional isomers. Now, for compound A, write down the homologous series to which it belongs. So we go and we look at A, and we say, okay, if we look at A, here, A is, we see the functional group is the carboxyl functional group, carboxyl. So the homologous series is going to be the carboxylic acids. So the answer is carboxylic acids. Carboxylic acids. The structural formula of its functional isomer. So when it refers to its functional isomer, it is referring to its functional isomer in this table. So if we look here, we have got a carboxylic acid. So if we're looking for a functional isomer, then we are looking at an ester. Now the question is, do we have an ester in this table? And when we look here, we see that A is a carboxylic acid, B is an alkene, C is a ketone. What did we say D was? D was an alcohol. We can see that E is an alkene. F is a ketone with a methyl group. This was a alkane with a methyl group and with halogens, and this is a aldehyde with a branch. So we do not find an ester in this particular table. So this is a bit ambiguous. If there was an ester with the same amount of carbons, we would have then looked in the table, but they're not there. I would have preferred for it to have been a bit more explicit, but we use reasoning, so we are looking for the structural formula of A. So we have got, if we look here, we have got a carboxylic acid, which happens to be ethanoic acid. So its functional isomer is also going to have 2 carbons, and it's going to be an ester. So we're going to have a carbon, and we're going to have another carbon. So this carbon is going to have a double bond O, and it's going to be bonded to an oxygen, and that oxygen is connected to a methyl group. So this would have come from methanoic acid. This would have come from methanoic acid, so this would be methanoate. And if we use the circle test, 1, 2, 3, 4, we are missing a hydrogen. So this would be, if we look carefully here, we can see, my apologies, this is actually incorrect. This would not come from methanoate. This would come from methanol. Apologies for that. This would come from methanol. Methanol, because it doesn't have the C double bond O. This comes from methanoate. This comes from methanoic acid. So this would be methanoate. Apologies for that. So this would have come from methanoic acid, and this would have come from methanol. And so, therefore, the name for this part of the ester would be methyl. So this would be, they ask, what is the structural formula? They haven't asked us for the name, but the name would be methyl methanoate. Methyl methanoate. Right, so 2 marks. That would be 1 mark for the methyl, 1 mark for the methanoate part of the molecule. Compound D undergoes a dehydration reaction. Now, at this point, we haven't done reactions in detail, but dehydration basically means the elimination of water, elimination of H2O. Right now, if compound D undergoes, if we look at D now, and we look at D and we see that D is in actual fact an alcohol, right? If we had to eliminate that, then this is actually going to produce an alkene. Now, for you as grade 10s at this stage that haven't done the organic reactions, we would not ask you this in your exams. So this would be unfair. But in a matric final exam, you would have already done the different types of organic reactions. So IUPAC name for D, if we look at D, right, well, D, we've already worked out is ethanol. So we can see here meth-eth with the hydroxyl group, so this is ethanol. So we can answer that this is ethanol. So the IUPAC name for D, this would be ethanol. We can answer it here. And then the letter that represents a product of this reaction. So I don't want to go into too much detail, but if anyone who's not, if someone is in matric and they are looking at this video, then they would understand this, or should understand this. We have got a ethanol molecule, and there is the hydroxyl group that makes it an alcohol. So what happens in a dehydration reaction, an elimination reaction, the OH and a hydrogen from the adjacent carbon, they leave, and in leaving, it results in a double bond forming, and so we go from a saturated to an unsaturated compound, leaving us with an alkene and an eliminated product, which would be the water, which is HOH. So this would be an elimination reaction, and the letter that represents the product of this reaction would obviously be E, because that's ethene. So this would be ethene, so the answer would be E. This is for only 1 mark. There is normally a separate question on organic reactions, but every now and then they integrate an organic reaction question into question 2, which is predominantly focused on organic structure naming. The name or formula of the inorganic reactant that is used in this reaction. Now, this is completely unfair for grade 10s, but what this would be a concentrated solution of either a concentrated solution of a base like sodium hydroxide. But if we look here, this is an alcohol. So if we are going to rip water out of an alcohol, then we are going to use sulfuric acid. So this would be a concentrated solution of sulfuric acid. because sulfuric acid is a dehydrator. One can also use a concentrated solution of phosphoric acid, and that would have a formula of H3PO4. So they've asked us to give the name or the formula of the inorganic reactant that is used in this reaction. So as a rule, and this is for grade 11s and 12s who've already done organic reactions, that when you are trying to eliminate water, then you use a concentrated solution of either sulfuric acid or phosphoric acid. When you are trying to remove something else, let's say for instance there was a bromine or a bromine in the place there, or chlorine as the substituent, then you would be looking at using a concentrated solution of a strong base like potassium hydroxide or sodium hydroxide. So I hope that this video lesson has helped you to at least give you a foothold into approaching these questions when you encounter them in tests and exams. They can seem quite intimidating because there's a lot of different organic compounds that you've had to deal with, especially with us doing it in grade 10. It's the first time you've encountered all of them. So there's a lot of information that is required to be integrated. But once you start practicing these, you'll find soon enough that it's not as intimidating, and hopefully this video lesson has given you a basic idea on how to approach these problems.